Okay, so what we're going to do in this video is we're going to see how we can come up with a numerical approximation to solve Poisson's equation on the unit square, and we're going to have these u equals 0 on the boundary. And again, I just want to emphasize this is not a numerical PDE class or any type of PDE class, so we're not going to get into a whole bunch of theory on PDEs or the numerical solutions to PDEs. The thing that we're doing in this class is learning how to solve large, sparse systems using iterative methods, and a lot of those systems are motivated by PDEs. So this is just sort of the area in which we're working. And it's much more interesting than just being like, solve these large systems without any context, because the shape of the systems and the fact that they're sparse are influenced by the things that are being modeled. I also think it's interesting to I think it's just an interesting thing as well, and I hope you do too. Anyways, so this is the equation that we want to solve. Minus the Laplacian of u is equal to f. As we will see, approximating the derivative is not going to be a challenge. It's going to be just applying what we saw in one dimension, but in two dimensions. But there are going to be some irritating things that we have to deal with when assembling the corresponding matrix. It's nothing we can't get over, but there are things that are just not as straightforward in the two-dimensional case as they were in the one-dimensional case. So let me just remind you that the minus Laplacian, or the Laplacian operator, is simply the double x derivative plus the double y derivative. So the Laplacian is simply the double x derivative plus the double y derivative. And so when approximating the second derivative, the most straightforward thing to do is just to do the one-dimensional x approximation and add that to the one-dimensional y approximation. In other words, the Laplacian of u, evaluated at the point xy, is going to be roughly equal to the following. It's going to be equal to u. I'm going to hold y fixed and kind of do the derivative in the x variable. So we're going to have x plus hy minus 2 u of xy plus u of x minus hy. Okay, now I see that I'm going to run out of room, so I'm just going to rewrite this all below. Okay, I'm going to write it all across here. So the Laplacian of u of xy, again, I'm going to do the variation in the x variable. So we're going to have u of x plus hy minus 2 u of xy plus u of x minus hy. Okay, that is going, once we divide by h squared, that's going to be the approximation to the double x derivative. And now the approximation to the double y derivative, we're going to have u of x y plus h minus 2 u of xy plus u evaluated at x y minus h. And then all of this, like this term here is going to get divided by h squared. This term here is going to get divided by h squared. And so we're just going to divide both of them by h squared. Now, one important thing to mention, it's not going to be something that matters in this problem, or in this class is not going to be something that matters. We're obviously going to be applying this to a grid, and the grid spacing in between the x points could be different than the grid spacing between the y points. And so this value of h for the x differences could be different than the values of h for the y differences. Okay, in principle, for us, it's all going to be the same. But now, look, we can simplify this a little bit. We have minus 2 u of xy here and minus 2 u of xy there. And so we can combine those into one sum, or into one thing. So we're going to have u of x plus h, y, plus u of x minus hy plus u of x y plus h, and then u x y minus h, and then minus 4 u evaluated at xy, and then all of this divided by h squared. Okay, and so now, again, this is just the one-dimensional approximation done in the x direction and the y direction and added together, because that's exactly what the Laplacian is. So the approximation here is very straightforward. Now what I want to do is I want to move this into a grid that we're going to put on this square 0, 0, 1 by 0, 1. So let me do that now. So let's say, the x-axis, this is 0, and this is 1 on the x-axis, 0 to 1. On the y-axis, this should be a square. It looks like maybe, I'm going to take it into maybe here, and we get something that's close to a square. And we're going to have in is equal to 4, so we're going to have a point here, and then 1, 2, 3. So 1, 2, 3, 4 equally spaced points here. This is x0, x1, x2, x3, and then that's x4. So x0 is equal to 0, but then going up this direction, 1, 2, 3, this will be y0, y1, y2, y3, y4. These labelings, as we will see, are not going to matter so much. All right, so now I'm going to sort of, you have all of these grid points. So if I draw, let's see what color I want to use. If I draw lines, I'm going to do dashed lines like this. Okay, and then this way. Wow. Okay, so we have 5 points going this way, 5 points going this way, and so there are 25 different grid points. And so the goal is that we want to approximate u as each one of these grid points. So similar to what we were doing with just the interval, approximating u at each one of the grid points on the interval, we want to approximate u at each one of these grid points right there. Now, the good thing is the boundary conditions say that u is equal to 0 on the boundary. So we know what u is along here, 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 and here. Okay, so the grid points that we don't know about are going to be the ones that I'm kind of going to put a circle at. So we don't know u here, or we don't know u before doing the solution. Here, here. So we're going to get 9 of them. Okay, so we're going to have a system with 9 unknowns. So we're going to have a system here with 9 unknowns, and we want to get a system. We want to drive a system of equations that's going to let us approximate u at each one of these points. Because again, here, 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 and here, we know that u is going to be equal to 0. Now, here's where, well, before I get to one of the issues, let's see how the difference approximation is going to work. So let's say that this point right here is it is the kth row, so 1, 2, third row, and the jth column, 1, 2 column, the second column, or the first, second row, and the second column, because only these green points right here that are sort of in our mind about what's happening. So again, whether we want k and j to include counting the bottom row and the first column is not going to matter, but we have some generic point ukj here. And the second order approximation then is going to say something like the following. Just note that k represents the row that we're on, and j represents the column. So the second derivative at this point, kj, okay, I need to go 1 to the right, 1 to the left. So I'm going to have u k j plus 1 plus u k j minus 1. Okay, and then I'm going to do plus, I need to go up and down, so plus u k plus 1 j plus u k minus 1 j, and then minus 4 u of kj, and then all of this divided by h squared. And if I have a minus sign here, I get a minus sign there, and then this for the system of equations, I set this equal to f kj. That is f evaluated at that point there. Now, there's obviously, if we look at this right here, if, for example, j is equal to 1, and it's right here, then j minus 1 is going to be equal to 0. So, like, this formula works for all of these grid points here, but just for some specific ones of them, like, j is equal to 1, we know that this term is going to be equal to 0. Okay, but here's where an issue comes up. The issue is that we need a way to give an ordering to our variables. In one dimension, it was very simple. We did u0, u1, u2, u3, u4, so on and so forth. u3 was just equal to u evaluated at xk. But now we don't just have like one index, we have two indices. So what can we do for that? So we need some way to order the vertices. We need to put in order on these vertices. Now, in principle, we could pick any order that we wanted to. I could say I'm going to index this variable, the u evaluated here, I'm going to call this u sub 1, and then I'm going to call that u sub 2 and that u sub 3 and so on and so forth. In principle, we could do that. Obviously, that doesn't make any sense. So the typical order is to do what's called the lexicographical order, which is to imagine these ordered pairs as like a word, and then do like the alphabetize, do the same order as alphabetizing. So like the word apple comes after the word ape in alphabetical order because they both start with A. P is the next letter for both, but then for ape, E is the third letter, which comes before the alphabet, then the third letter of apple, which is P. Or apple apple comes before the letter bear, because if you look at the first letters, A is bigger, or A comes before B in the alphabet. Same thing here. So like this point is going to come before this point because the x coordinate is bigger than the y coordinate. But this point is going to also come before this point because even though the x coordinates are the same, the y coordinate is smaller. Okay, so what this works out then is I'm just going to write out what these orderings are going to be. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So then what we have then, if we look at this and use these orderings to give us the approximations, minus, let me write it up here, minus u5 double prime, so the second derivative evaluated here is going to be approximately u6 plus u4 plus u8 plus u5, u2 plus u2 minus 4 u5 divided by h squared. And in the approximation, we would set this equal to f sub 5, which is f evaluated there. Okay. So now our ordering, though, because we have this different ordering, we have to figure out what is a formula going to be, because we can't just add 1 to the second index and add 1 to the first index or things like that. We only have that one index, so we have to figure out what the general formula is going to be. Okay, so let's do that now. So for the kth equation, okay, that is the equation where we have the right-hand side is going to be f sub k. So let's imagine that k is equal to 5, for example. What is the approximation going to be? Well, we're going to have the second derivative over here. Okay, so I need to go 1 there and 1 to the right and 1 to the left. So if I just look at 5 as an example, I'm going to have u k plus 1, that's going to advance me 1 to the left. If I do uk minus 1, that's going to, uk plus 1 advances 1 to the right. Uk minus 1 goes 1 back to the left. Some of you might be saying, like, wait a second, there's going to be a problem. And you're right, there is going to be a problem. What about this? I need to go up. So what is the thing there? Well, 8 minus 5 is 3, and that's the number of interior points. And that's the general pattern. So if I want to know the point right above it, it's just going to be the index plus, in this case, n minus 1, which is 3. So it's always going to be this plus n minus 1. So we're going to have u k plus n minus 1 plus u k minus n minus 1. That's going to give me this. And then minus 4 uk. And this is going to be equal to h squared fk. Okay, so this is going to give me the approximation. Now this right here, we call this the 4-point stencil, or sorry, the 5-point stencil, the standard 5-point stencil. So this is what the stencil looks like. We're using these 5 points, but there's other stencils that we can use as well. We could use these diagonal points instead of these points, or we could use the diagonal points in conjunction with these points, and there's all sorts of different things. But the main one that we're going to use, in fact, the only one that we're going to use is this 5-point stencil that we have here. And I didn't say it before, let me say it now. The 5-point stencil looks like this. Okay, meaning in the difference approximation, we take minus 4 here and then 1 on all of those. Okay, like I showed you what the 3-point stencil was on the line, or for the interval. Okay, so what are the issues that we could have here? Well, what if my index is here? What's going to happen? If I add 3 to this, I'm going to be 11, so that doesn't exist. So that doesn't really give me a problem. It's kind of like I'm going outside of where the matrix is. So if I add 3 to this, maybe like in this formulation, I'll get something kind of weird and undefined. But in terms of the matrix that we're going to build, this is not going to give us a problem. And similarly for things on this row. Where the issue comes is like for U4. Because if we take k is equal to 4 over here, what are we going to get? Well, we'll be okay here because we're going to get 1 and 7, U1 and U7. But notice when I do k minus 1, it's not going to take me here. If it took me there, that wouldn't be a problem. Okay, the issue is that when I do minus U3, it's going to take me down here. And so now I'm computing a derivative here, but using this point way over there, which doesn't make any sense. So this is the problem. So what we're going to do is we're going to forget about that problem for a minute. We're going to build a matrix using this part right here, just this formula right here, and then try to figure out the ways in which we need to make up for this problem that I just mentioned. And it's only going to be for these points right here. Okay, like we'd have a similar problem for 6. If you add 1, you're going to get up to 7, and now there's no reason you should be using those in the same approximation. Okay, so what is the matrix going to look like? Well, a couple of things to point out. There are 9 unknowns, so it's going to be a 9 by 9 matrix. But what I want to do is I actually want to write down this matrix explicitly so we can get an idea of what's happening. Now, it's a 9 by 9 matrix, so it's going to be a big matrix, okay? It's a 9 by 9 matrix. It's going to be a big matrix, and it's going to take me a little bit. It's going to take a long time for me to write this down, but I think if we do this, we'll get an understanding of what this matrix is going to look like and how we can better implement it in code. So watch this part on twice speed if you want to or something. And like I said, it's a 9 by 9 matrix, so it's going to take me quite a bit of time to write it all down. That's a total of 81 entries. And I'm hoping that I'm going to be able to do this neatly enough, okay? All right, so let's look at the U1, or the equation corresponding to U1. So let me just put here on the right-hand side, we're going to have h squared times f1, f2, f3, f4, f5, f6, f7, f8, f9. Okay, and so now I want to know what the first row is. That's going to be corresponding to the first equation, the F1 equation. So if k is equal to 1, if I look at this formula, what's going to happen? Okay, well, let me go on ahead and distribute these minus signs so I don't get confused. So minus sign here, minus sign there, and a plus sign there. Okay, so k is equal to 1. I'm looking in the front row. K is equal to 1. What is the coefficient on U1? This is the first column. So if I look where k is equal to 1, what is the coefficient on U1 going to be? Well, it's going to be equal to 4. So I'm going to have a 4 here. Okay, what about U2? What will the coefficient on U2 be? Because that is what this is here. So what will the coefficient on U2 be? Well, k is equal to 1, so this is going to give me U2, so I'm going to have a minus 1 here. What is the coefficient on U3 going to be? Well, am I going to have a U3 over here? No. This is n is equal to 3. Sorry, n is equal to 4. So n minus 1 is equal to 3. Let me just go on ahead and make this 3 so I don't keep forgetting. K plus 3, 1 plus 3 is 4, and 1 minus 3, this is going to be 0. This goes off of the grid. So we're going to have 0 for the coefficient on U3. Okay, now U4, there is going to be a coefficient on U4. The coefficient on U4 is going to be equal to minus 1. And then all the other ones are going to be equal to 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now if I go down to the second row, this is going to correspond to the second equation. So what's going to happen for the second equation? Well, for the second equation, if I do my 4-point stencil or my 5-point stencil, the coefficient on U1 should be a minus 1. The coefficient on U2 will be a 4. The coefficient on U3 will be a minus 1. Okay, there's this coefficient on U4 is a 0 because that's not part of this stencil. But the coefficient on U5 should be minus 1 as well because that's part of this stencil. And then it's only, for 2, it's only these 1, 3, and 5 where there's going to be a non-zero coefficient. So then we're going to have 0, 0, 0, 0. Okay, moving up to U3. Well, what's going to happen? The 3-point or the 5-point stencil only includes 3, 6, and 2. So we're going to have 0 for 2. We're going to have a minus 1 for 3. We're going to have a 4. For 4, there's not going to be anything. For 5, there's not going to be anything. And then for a 6, there's going to be a minus 1. I feel like I'm writing my rows too big. And then it's going to be zeros everywhere else. So, okay, first row, we're done with. Perfect. Okay, now let's look at U4. U4 is going to be where another interesting thing happens. So let me go back actually to U3. If we look at U3 and follow this formula exactly, if we look at U3 and follow this formula, hold on 1 second. If we look at U3 and follow this formula exactly, k plus 1 is equal to 4. So 1, 2, 3, 4, I should have a minus 1 here. Okay, there should be a minus 1 right here. Now I'm writing it in red because this is not right. Like according to this formula, there should be a minus 1, but we need to change our formula for these, for the entries here and for the entries here. But so far, this formula and this formula, whether or not we deduced it from just looking at the grid here and thinking what the stencil should be, or just blindly plugging things into the formula, we got both of these rows sort of doing it just by looking at this and seeing what the stencil is and applying the formula gave us the right thing. For this row right here, and we're gonna see this for the next row as well, what's gonna happen is that doing the approximation from the stencil and doing the approximation from the formula are going to get us two different things because we need a secondary sort of correction for when the grid points are here or here. Okay, so let's do that now. And the red ones are going to be where the errors are. So the errors are where the formula gives us something that the grid does not give us, and we'll have to see how we can fix that. Okay, so next for U4, again, if I look at the stencil, what's going to happen with just the stencil? Well, the coefficient on U1 is going to be a minus 1. The coefficient on U2 is going to be 0. The coefficient on U3, this is where where a correction, well, this is where the formula is going to give us something different. So I'm going to have a minus 1 here. I'm going to have a 0 for U2. For U3, according to the stencil, this should be equal to 0, but we'll see the formula is going to give us a minus 1 here. 1, 2, 3, 4, we're going to have a 4. U5, we should have a minus 1 as well. and then everything else is going to be 0, both according to the stencil and according to the formula. Okay, but again, for k minus 1, if k is equal to 4, k minus 1 is going to give us 3. So according to the formula, we should have a minus 1 here. Now the formula does not match up with what is actually true, and again, that's just one of the issues that we're going to have to resolve in some way. But for now, I just want to write in here what the formula gives, and just in red, I'm going to say where that formula is wrong. Okay. Now what about for U5? So we're on the 5th row here, the 5th equation. Well, in this case, the formula and the stencil are going to give us the same thing. So the coefficient on U1 is 0. The coefficient on U2 is minus 1. The coefficient on U3 is 0. The coefficient on U4 is minus 1. The coefficient on U5 is 4. The coefficient on U6 is minus 1. The coefficient on U7 is 0. The coefficient on U8 is minus 1. And then the coefficient on U9 is 0. Hold on. Something. So for U4, the coefficient on U1 is minus 1. The coefficient on U2 is 0. The formula gives an incorrect coefficient of minus 1 here. For U4, we get 1. For U5, we get minus 1. Oh, and then for U7, for U4, for U7, we're also going to get a minus 1. Okay, there we go. So this is 1, 2, 3, 4, 5. Okay, now let's look at the 6th row. Again, we're going to have something happening here that we need to worry about. So again, if we just consider what the stencil says, there's no coefficient on U1. There's no coefficient on U2. The coefficient on U3 is going to be equal to minus 1. The coefficient on U4, again, just looking at this, the coefficient on U4 is 0. The coefficient on U5 will be minus 1. The coefficient on U6 will be 4. The coefficient on U7 is 0. The coefficient on U8 is 0. And the coefficient on U9 is minus 1. Okay, however, if you look at the formula, k plus 1 is 7. So U7 should have, according to the formula, a coefficient of minus 1. So 1, 2, 3, 4, 5, 6, 7. Minus 1 like this. And again, the whole point is that that minus 1 is not correct. The formula gives it. If we just blindly apply this formula, we would get a minus 1 there. If we just blindly apply that formula, but according to this, there should not be a minus 1. According to the stencil, there should not be a minus 1. The stencil tells us what is exactly correct. This formula will have to be modified, and subsequently the matrix will have to be modified to take care of these entries here. Okay. So that was U6. If we do U7, again, if we just look at what the stencil says, the coefficient on U1 is 0. The coefficient on U2 is 0. The coefficient on U3 is 0. The coefficient on U4 is minus 1. The coefficient on U5 is 0. The coefficient on U6 is 0. The coefficient on U7 is 4. I was not writing things down. Okay, let me start over for U7. For U7, the coefficient on U1 is 0. On U2 is 0. On U3 is 0. On U4 is minus 1. On U5 is 0. On U6 is 0. On U7 is 4. On U8 is minus 1. And on U9 is 0. Okay, but however, if we just apply this formula here, k minus 1 is equal to 6. And according to the formula, there should be a coefficient of minus 1 on U6. So we're going to have this right here. Okay, good. Now, the 8th row, what are we going to get? Well, again, this one, the formula and the stencil are going to give us the same thing. The coefficient on U1 is 0. The coefficient on U2 is 0. The coefficient on U3 is 0. On U4 is 0. On U5 is minus 1. The coefficient on U6 is 0. The coefficient on U7 is 1. The coefficient on U8 is 4. And on U9 is going to be minus 1. Okay. And then finally, when we look at the ninth equation, the coefficient on U1 is 0. On U2 is 0. On U3 is 0. U4 is 0. U5 is 0. The coefficient on U6 is minus 1. The coefficient, according to the stencil, on U7 is 0. The coefficient on U8 is minus 1. And the coefficient on U9 is equal to 4. However, 9, yeah, sorry, let me stand up here. So according to the stencil, what is going to be, we're going to have this one and this one. When we do minus 1, we're going to get 8. When we do plus 1, we're not going to have the problem for this one. When we do plus 1, we're going to go here, which would give us U10, which puts us outside of the grid. In other words, U10 is equal to 0, and so the coefficient of U10 is always going to be equal to 0 because U10 is equal to 0. Similarly, for U1 here, when we did minus 1, we are going to U0, but U0, if we want to think about that point right there as being U0, is equal to 0. Okay, so now what we have is we have the rows corresponding to 4, 7, 3, and 6. So this is the third row, and this is 4, 5, 6, 6, and 7. For those rows, what happens is that we have these extra minus 1s that we need to get rid of. But let's look at the structure of the matrix. Let's look what this tells us. If we just apply this formula and forget about these corrections, what does this tell us? Well, if we think back to how we did this for one dimension, if we're looking at the kth equation, the coefficient on UK tells us what the diagonal should be. So the diagonal is going to be all 4s. So we have a diagonal along the diagonal. Obviously, if I could draw this matrix a little bit better, it would be clear that that's a diagonal. Okay, UK plus 1. The minus 1 that's on the UK plus 1. This tells us what is on the 1. I'm going to call it the 1 super, meaning the 1 super diagonal. Okay, that is the diagonal above the diagonal. This tells us that the diagonal above the diagonal should be minus 1s. And that's what we get here. Okay? This right here, k minus 1, this tells us what the coefficient is going to be on what I'm calling the minus 1, or sorry, the 1 subdiagonal, or the first subdiagonal, meaning the diagonal directly below the diagonal. So that's what we have here. We're going to have minus 1s here. That's the diagonal below the diagonal. K plus 3, okay, so this right here, k plus 3, is going to be what is on the third super diagonal. So it's not the diagonal above the diagonal, or the diagonal above that. That'd be the second diagonal, but the diagonal above the second diagonal is going to give us the third diagonal. So again, this is the first diagonal, this is the second diagonal, and then this is the third super diagonal. Okay, and similarly, this is going to be the third subdiagonal. So this is the first subdiagonal, this is the second subdiagonal, this is the third subdiagonal. And it's just going to be the parts corresponding to the first super and the second subdiagonal where we're going to have any issues at all. And we can actually kind of see how we can break this matrix up conceptually kind of into 3 different pieces here. Something like this, right? We have this and then a block here and a block there with off diagonal entries as well. Maybe I'll just forget about that part. If you look at the sparsity diagram, that will make a lot more sense. So one of the things that you're going to do in the homework is to look at a sparsity diagram for something like this. In the homework, I'm asking you to do it for fairly large values of n, but just for your own sort of learning purposes, do it for a smaller value of n, like n equals 3 or 4 or 5, to see what the sparsity diagram is going to look like. Okay, so now what we have to do then, just looking at the matrix, we see we have these minus 1s, and we can just get rid of these minus 1s, right? In code, how are we going to implement this? Well, implementing these implementing these matrices right here, if you didn't have to worry about the red part, we can implement these matrices pretty fine using the numpy EYE function. So this would be like 4 times EYE. We have a 9 by 9 matrix here, so this would be 4, let me just write it out. We're going to get something like 4 times EYE of n minus 1 squared, because n is equal to 4, n minus 1 is 3. We have an n by n matrix, so it's going to be like this. And then we're going to do something like minus EYE, and then we're going to do n minus 1 squared, k is equal to 1. That's going to give us the first subdiagonal, or the first superdiagonal. And then minus EYE n minus 1 squared, k is equal to minus 1. And then minus EYE n minus 1 squared. And remember, that 3 and that 3, that's n minus 1. So we're going to say k is equal to n minus 1, and then minus EYE n minus 1 squared, k is equal to minus n minus 1. That's going to give us this matrix there, but with the red entries are also going to be minus 1. So then one way that we could do, we have this matrix right here. One thing that we could do is we could do a loop. Okay, so we need to look through the values 1, 4, and 7, 3, 6, and 9, and do something like the following. So we got to have a loop that goes something like the following. For k in range n, do the following. So range n is going to give us 1, 2, 3, all the way up to n minus 1. So in this case, it's just going to give us 1, 2, 3. And then what we can do is we can say, okay, for the corresponding entry in the matrix, make it 0 when it needs to be 0. Okay, and we will implement this. I will implement this and show you how to do this exactly in the labs. But I'm not going to write this right now. But this is just a sort of type of loop that we would want to go through. So I guess, if we look to see what the pattern is, I will talk more about that in the lab on how to actually implement it. But it's going to be, it's going to be 1 plus n minus 1 plus n minus 1, and then n minus 1 plus n minus 1 plus n minus 1. Those are the 3 rows that we're going to have to think about. And then even that, we have to make an adjustment to the adjustment because we don't need to adjust 1 and 9. Anyways, okay, so this is a brief guide on how we can build our system of equations to approximate the solutions for Poisson's equation on the square. This is sort of the theory behind it. It's not really theory, it's just sort of the construction of the matrix, by hand. And then I will show how we construct that matrix in the labs, different ways that we can construct that matrix using Python code. Because there's sort of a way like this that's very explicit, and then there's a slightly slicker way, but I think sort of hides some of what's going on, which is fine, it'll be faster, but teaching-wise I want to do this first.